All right, so now we're going to move on to lesson 4.4, which is dealing with the quadratic formula, which is actually our third and final algebraic method to solve quadratic equations. So up to this point, we had factoring, which was one method, and we had reviewed that a ton, including our chapter 0 notes. We then moved into our complete the square, which was an actual method that was introduced in our unit 1 quadratic functions. Now we're going to put in the quadratic formula, which is this nice formula that offers us another algebraic way to solve quadratic equations. Okay, to start up this lesson, we're going to start by doing the previous ones that we would have talked about. So in 4.1, we would have talked about using graphing technology to solve these. And so we're going to take this and plug it into our graphing calculator. In fact, what you're going to do is you're going to take all of this stuff on the left-hand side here, and you're going to throw that into your y1 in your calculator. And then for the 0, what we could do is if you're wanting to do the intersection method, we could plug this into our y2 in our calculator, and that would give us the ability to find the intersection. But if you're just going to use the zeros or roots part on your TI or Casio, then all you need to do is type in the y1 section, which is the 3x squared plus 5x minus 2. Now, graph this using the technology at your disposal. So the Casio or the TI calculator, hopefully. Now, what I'm going to give you is some window settings off and to the right-hand side here. First and foremost, we're going to deal with our X and Ys. So I'm going to put X's here and my Y's here. For my window settings, we always start with our minimum. So I'm going to write -5 for X. I'm going to write 3 for the maximum for X, and then a scale factor of 1. I'm going to write -5 for the Y's, +5 for the Y's, and then 1 for the scale factor. Now again, in our graphing calculator, we want to rewrite this function. So what we're going to do is in y1, we can type in 3x squared plus 5x minus 2. In y2, if you're wanting to do the intersection method, you could put in 0, and this is going to create a horizontal line where y is equal to 0. And now, here's the rough sketch that we're going to get in our graphing calculator. Once we plug in these functions or plug in these equations to our graphing calculator, we also set our window to the appropriate settings based on what I've given you here. We should get a graph that kind of looks like this, where we're going to have it cross on the left axis or negative axis one time. Then it's going to come back up and through in the positive side, and we're going to put arrows on the end. Now, this might not be 100% accurate in terms of the overall sketch, but it's definitely going to do us justice. It's going to be close enough. Now, what we're going to do is we're going to put a dot on our two x-intercepts, or what we call our roots or solutions. So one x-intercept on the left, one x-intercept on the right-hand side. Now, what I'm going to do is I'm going to write in our graphing calculators, we know that we can do second trace 0 if we have the TI graphing calculator, or if we put in this y2 being equal to 0, you can go second trace intersect and solve for these. If you have the Casio, you're going to click Shift G solve and then root if you want to solve it using the x-intercept method, or Shift G solve and then your intersect, or ISCT or ICST. All right, now if we do that, it's going to give us -2 for our x-intercept on the left, and our positive x-intercept is going to be 1/3 and 0. There we go. And we're writing it as an ordered pair to represent it's a point on the graph. So therefore, using graphing technology, our solutions for x are x is equal to -2 and x is equal to 1/3. And you could write it as just x equals and then put the value comma the other value, but sometimes I like to write it like this. I'm going to highlight this because this is our solution. Now, let's factor this instead. So taking the exact same equation, what I'm going to do is then I'm going to rewrite it as 3x squared plus 5x minus 2 is equal to 0. We need a number that will multiply to make 3 times -2, which is -6. And then if it must multiply to make -6 but add to make +5, that means our number that we're going to replace here is 6 for our one number, so 6x plus, or in this case, minus 1x minus 2 is equal to 0. Because if I multiply 6 and 1 together, or 6 and -1, this gives me -6. You add a +6 to a -1, it gives you this 5 that we wanted as our middle term. Now we know at this point we need a factor by grouping. Factor by grouping, I'm going to take the first two, underline them, the second two, underline them. When I do this, I realize that I can remove a 3x from the first, leaving behind with x plus 2. In the next grouping, I mean, there's nothing I can really remove other than the -1. Because if there's a negative on that third term, try to remove it. This is going to leave me with x plus 2 once I've divided both sides by the -1. All right, now what I'm going to do is I'm going to pair together my outside terms. So it's going to be 3x minus 1 in one bracket, And then I'm going to take one of those common binomials, x plus 2, and set this all to equal to 0. Now, we know from our previous lessons, at this point, we're going to take our different factors and separate them, both being equal to 0. So x plus 2 equals 0, and 3x minus 1 equals 0. If we algebraically isolate the left-hand equation, well, we're going to add 1, and then we'll divide by 3. It'll be 3x is equal to 1. We divide both sides by 3. This gives me x is 1/3. Okay, that aligns to our previous solution that we got using our graphing calculator. Now let's go over here and just make sure our second solution is good. We're going to subtract 2 from both sides. Therefore, x equals -2. In fact, this was the other solution. Therefore, we now have a method showing it graphically. We now have a method using it algebraically, which is our factoring method. Now, let's do our second algebraic method, which is completing the square. We're going to take that same trinomial, and then instead of factoring it and graphing it, we're just going to do our other method from Unit 1, quadratic functions. So I'm going to take the 3x squared plus 5x minus 2 is all equal to 0. And we look at this and we're like, is there a common term in these first two? Because what we want to do is separate these in brackets. So take those first two terms, starting with the x squared term and the x. We're going to put brackets around them. You look for a GCF, and in this case, there is no GCF or greatest common factor. So now we can go right into the b divided by 2 step and square it. This is going to be 5 divided by 2 all squared. Well, 5 divided by 2 is going to give us a decimal. More importantly, it's going to give us 2.5. So we're going to keep it exactly as is, and then I'm going to square it from here. So this is going to be, oh, and you know what we're going to do? We're actually going to remove out the factor of 3 from here, because realistically, we want to have that x squared isolated. So if we have the 3 still in there, it's not going to be good for us. Let's take that 3 out and write it as x squared plus 5 over 3. We're dividing both terms by the 3. The 2 on the outside is just left alone because it wasn't a part of the first 2 pairing here. Now what we can do is our b divided by 2, because we always want to leave that x squared alone as a coefficient of 1. And so try to pull out whatever's in front of that x squared term when we're completing the square. Now we're going to take this and go b divided by 2 all squared. This is going to be equal to 5 over 3 all divided by 2 squared, which is the same as 5 over 6 squared, which is equal to 25 over 36. Okay, now we're going to plug this back in. So it's going to be 3x squared plus 5 over 3x plus 25 over 36 minus 25 over 36, and then close the bracket, minus 2 equals 0. Now we know if we want to remove out this negative term, we must multiply it by the coefficient because it's attached to this 3. So we're going to rewrite this as 3x squared plus 5 over 3x plus 25 over 36. And then close the bracket. We're going to write this as negative 25 over 36 multiplied by the 3 that was out front, minus 2 is equal to 0. This is now going to give us 3x squared plus 5 over 3x plus 25 over 36. Close the bracket. Now, 25 over 36 times 3, the 3 and the 36 are going to reduce down to 1 and 12, so we can make this 25 over 12. And then if we combine those two factors together, the 25 over 12 minus the 2, this is going to give us negative 49 over 12. Now, that's us combining together this and this. When we take our negative 2 and we subtract the 25 over 12, that combination gives us negative 49 over 12. Now, this is going to be equal to 0. Now, we can take this a step further. Let's go off onto our right-hand side and continue this. Remember, instead of this trinomial, we actually know it factors down to a specific term. That term includes the b divided by 2 value. So we should almost highlighted that earlier, but we'll go back and just make sure we have that. The b divided by 2 value before it's squared is the perfect square trinomial, or that piece that makes up the p-value of the vertex. So we're going to write this as 3 bracket x plus 5 over 6 all squared minus the 49 over 12, which was on the outside, is equal to 0. Now, before we can do anything with this term in terms of getting it alone for x, we must add the 49 over 12 to both sides. So we're going to go plus 49 over 12 plus 49 over 12. That's going to add it to both sides, leaving us with 3x plus 5 over 6 all squared is equal to 49 over 12. Now I'm just going to clean up that 3 a little bit. There we go. Now, In this case, we want to divide both sides by 3 because I want to get rid of that coefficient that's on this term here. That's going to leave us with x plus 5 over 6 all squared is equal to, well, 49 divided by 12 divided by 3. What happens is when there's two numbers in the denominator like this, or there's a term being divided and then another one below it, those end up being multiplied. So this is going to be 49 over the 36, because 3 times 12 gets us back to 36. Now what we're going to do is we're going to square root both sides of this equation in order to get x alone. So now we're going to have x plus 5 over 6 is equal to, well, the square root of 49 is equal to 7. Square root of 36 is 6. But remember, it must be the plus minus version of that. Please don't forget that. When we take a square root of a number, it is now going to be, by the square root principle, the positive and minus version of that exact term. Now we're going to separate this into the two cases. So I'm going to arrow up and do the first case. We have x plus 5 over 6 is equal to the positive 7 over 6. Now we're going to subtract the 5 over 6 from both sides, minus 5 over 6 minus 5 over 6. This is going to give us x is equal to 7 over 6 minus 5 over 6 is the same as 2 over 6, which is equal to 1/3. Oh, wait, this is really good. We're confirming exactly what we got above. X was equal to 1/3, or positive 1 over 3 for one of the values. So this is really good that we're getting this. This is a good sign that we're in the right direction. Now we're going to take our other root, which was x plus 5 over 6 is equal to the negative 7 over 6. Now when we do our same step that we did before, we minus 5 over 6 from both sides because we want to isolate for that x. We're going to get x is equal to negative 7 over 6 minus 5 over 6. That's negative 12 over 6, which is the same as negative 2. Hey, look, we got our second solution, or our second root of the equation. Now, again, we have now shown two algebraic methods, one being factoring, one being completing the square. These are both at your disposal in terms of solving. Now, they could ask you for one of these in particular, but we now have an option of two different algebraic methods based on our previous lessons. We also have one non-algebraic method, which is the graphing method, typing it into your calculator, solving that way. Just be looking for that within the questions, because they may say you can use technology. In some of them, they may say factor or complete the square, or they might just say algebraic. You need to show all the work. Algebraic means basically you're showing top through bottom. You're not just simply giving me numbers from a calculator. You're doing some sort of algebra in order to isolate for that value. All right, now here's where we go into the new material. That was all review. 4.1, if we want to label these. Graphing, this was all 4.1. Factoring, 4.2. This one below, 4.3. Now what we want to do is go into the 4.4 material, which is our last algebraic method. Now before we get there, what we're going to do is we're going to complete the square on the basic trinomial, which is ax squared plus bx plus c, to show that we can actually derive the quadratic formula, or this final algebraic method, using this basic trinomial. So let's complete the square on this. And in this course, don't worry, I'm not going to ask you to do this. I would never ask you to reproduce a proof, because we're not in a proof-based course. That's more of a university level style course. Now, for this one, when we derive this, what we're going to have to do is we're going to take our trinomial of ax squared plus bx plus c. And when we completed the square, what we always did is we started by bracketing the first two terms, the x squared and the x term. Now we're going to do our b divided by 2 once we have this here. But before we do that, we must remove out a common factor. In this case, we want to leave the x squared alone, just like in all the other complete the squares. So we're going to remove out an a. This means it's going to be a with x squared plus bx over c, or bx over a, I should say, plus c. So we've removed out that common factor of a from both terms, aka we have to divide both terms in that first grouping by a. Now when we do that, we're now in a situation where the x squared is alone, so we can do our b divided by 2 all squared, b divided by 2 squared, which is equal to, our b value is actually b over a divided by 2 all squared, which is the same as b over 2a all squared, which is equal to b squared over 4a squared, because we know 2 squared is 4, a squared is a squared. Now remember, when we divide the middle term, or that b value, by 2, we want to make sure that we have it in terms of, we highlight it because we know it's going to reappear. Now, I know it's a little bit confusing when we say b divided by 2 because the b value is b in this term, but just be looking for it as it's the coefficient of the x term. So if the coefficient of the x term in this particular example is b over a, then we must put b over a divided by 2. Okay, now we're going to take this value and plug it into the trinomial. This is going to be a bracket x squared plus bx over a plus our b squared over 4a squared minus b squared over 4a squared, close the bracket, plus c on the outside is equal to 0. In the previous problems, if we wanted to take out this negative term, we had to multiply it by the a, or the coefficient out front. So this is now going to become a x squared plus bx over a plus b squared over 4a squared. Close the bracket. Now it's going to become this negative b squared over 4a squared multiplied by a plus c is equal to 0. Now I'm going to do two things in the next step here. I'm going to transform this trinomial into the binomial squared, making it the perfect square trinomial. And I'm going to see if I can combine some stuff here. Now, if I do this, it's going to give me a. In the bracket, remember our b divided by 2 term was b over 2a. So we're going to write this as x plus b over 2a all squared. And then on the outside here, we have a negative, so the term will be negative. A divided by a squared leaves one a in the denominator, so this is negative b squared over 4, and it's just going to be a instead, plus c is equal to 0. All right, perfect. Now, from here, what we're going to do is I'm going to create a common denominator with this term here. And by this term, I mean the one that is outside here. To create the common denominator, if there's a denominator of 4a, let's multiply this term by the 4a divided by 4a. And what that's going to allow us to do is put them together. So I'll even write that as a note here. If we want to combine both of these two here, what we're going to do is we're going to surround this and multiply it by 4a on the numerator and 4a on the denominator. And I'll even write that as a fraction there. Maybe I'll even separate the equals 0 way and just write that way neater just so it's actually in there, showing that we can make our common denominator. So 4a over 4a. If you multiply a term by 4a over 4a, you're technically multiplying it by 1. So we're not really changing the equation. We're just changing it to create some sort of common denominator so we can put terms together. Now, let's show how this comes together. It's a x plus b over 2a all squared. On the outside, it's going to be negative b squared plus 4ac divided by the 4a in the denominator, and this is all equal to 0. And the reason we have this 4ac is because we multiply c and 4a, and then the denominators would be the same, so we put them together, and there's our term. All right, perfect. Now, I just want to make sure that we have all the right terms here. So we have our negatives there, perfect. We have our positives in the right position, so that seems okay, awesome. I just want to make sure there's not any sort of lingering sign errors here that might cause this issues. So if we then add this across, yeah, this seems okay, perfect. Now, what we could do is we could remove out a, no, I think this is going to be okay. If we have this here, I just want to make sure that our signs were all okay, but it seems like they are. There might be one sign we have to change, but I think we're okay as is. What I think we have to do is I just want to double check the sign on C. The sign on C seems okay as is. What we could do is we could reverse it so that it is plus this, but no, we don't want to have that. If we combine these, we're going to be adding them. Yeah, that seems okay. Yeah, what I'm struggling on here is we should have a negative here. And so I just want to confirm that we should have that negative. Let's even look back to a previous step. So the positive c was on the outside. Okay, that was good. We had the negative come out, which was from the product of there. So negative was here. We now have this negative here. We had the positive here. We put them together. Good. Yeah, I'm not really seeing any issue with this. These two terms should be okay. The only other thing I think about here is that this was a negative term here. This might correct it for us. This was specifically a negative term, meaning this is actually written like this. Positive, this is a negative term. Yes, this will correct it. Okay, that's better. I was going to say, we're missing something in here, and that's going to throw us off, and we want to make sure this is specific, because I'm actually going to rewrite this using one more step before we continue. It's really important that this ends up turning negative You're going to see why just in a second. I'm going to rewrite this as a x plus b all over 2a raised to the power of 2. And then instead of this being a negative out front, what I'm going to do is I'm going to take that negative and place it here, and then that will change the sign in the middle here. So this is going to instead become a negative here, which will then make the b squared positive. It's going to make our 4ac negative, and then all divided by that common denominator of 4a, which is equal to 0. There we go. That's better. Because on this, we just need to be very careful with this. We're technically adding, when we combine these two together, the c and the 4a together like this, or the b squared and the c4a, we needed to be careful with what's happening with the signs. Okay, now what I'm going to do is I'm going to take all of this stuff on the right, or this stuff just outside of the squared, and I'm going to move it over to the other side by adding it. So our next step is going to look like the following. And let me zoom out and create enough space here. So on my left-hand side, I'm going to be left with a, in the brackets, it's going to be x plus b over the 2a, which was our b over 2, all squared, is equal to, we add that to the other side, or the b squared minus 4ac term that was originally negative, we now add it to the other side. This is still 4a. Awesome. Now we're going to divide by the coefficient term of a, divide by a. All right, now when we do this, it's going to leave us with x plus b over 2a, all squared, is equal to, on my right-hand side, we're going to be given b squared minus 4ac divided by, if I take 4a and I divide it by another a, this actually combines to make 4a squared. Because in this situation, if we did our reciprocal rule, we would find that these two actually multiply together. So 4a times a, this gives me 4a squared. Now what I want to do is square root both sides. So to square root both sides, here's what it's going to look like. I'm going to take the square root of the left, square root of the right. Now this is going to give us the following. We have x plus the b over 2a is equal to the plus minus version of the following, plus minus the square root of b squared minus 4ac divided by the square root of 4a squared is 2a. So we can't square root that top grouping because, and don't fall into the trap of square root of b squared like this. You can't individually do this. So if they're attached by addition or subtraction, you can't just do one part and then call this b instead of b squared. So keep it as is. If it's being added and subtracted, unless they both perfectly square, we have to leave them. Now, we get to this step here. What we're going to have to do is subtract the b over 2a from both sides. So when I subtract the b over 2a from both sides, as such, 2 or b over 2a, not 2 over ba. There we go. All right. Now this is going to isolate x is equal to, we get negative b over 2a as that front term, plus or minus, or in this case, we're going to write it as, yeah, I guess plus or minus is acceptable for this, b squared minus 4ac, all divided by 2a. Now, what we notice is there's a common denominator of 2a. So we can actually put these together and write it as x is equal to negative b plus or minus the square root of b squared minus 4ac. Let me make sure that's just a touch neater. There we go. All divided by 2a. Now, this is what we call the quadratic formula. So it is our final algebraic form, or our third and final algebraic form, where if we know the coefficients of a, b, and c from our trinomial, you can plug them into this formula. There you go. Now, on a test, before you use this, I would never say you have to derive the equation and then you can use it. No, in fact, this is actually given to you on your formula sheet. So the point of this activity was just to say that if I complete the square on that original basic trinomial with no sort of specific coefficients, I can actually derive the quadratic formula. And it's a really nice formula that gives us the roots, x-intercepts, or zeros to any given quadratic. Now, this is the one foolproof method. So if you're ever like, wait a minute, is there a trinomial I can't factor or complete the square on very easily? Always go to this. The quadratic formula is the one that's like the foolproof method in order to get your x-intercepts, roots, or zeros. So if you're ever like in doubt, use the quadratic formula, aka this formula we've just highlighted in green, which is going to be on your formula sheet. All right, let's actually use this quadratic formula. Again, we just derived that quadratic formula by completing the square on the basic trinomial. Here it is. Here's how you would see it on your formula sheet. Negative b plus or minus the root of b squared minus 4ac over 2a. You'll probably get so good at using this in this semester that you'll just memorize it after the first couple times you use it. Now, there's a couple of important things to look at here when using quadratic formula. First and foremost, it must be written in general form. Ax squared plus bx plus c equals 0. We need to have all the coefficients on one side of the equation. The other thing we need to do, identify the values of a, b, and c. Really, really important that you take time to be like, what is my a, what is my b, what is my c, including the signs of them. Then we're going to take the formula, write it out, and sub in our values. Finally, we're going to simplify the numbers and arrive at simplified roots or even simplified numbers. All right, let's see if we can try this out here. So quadratic formula, we're going to solve by using it. When we look at these examples, first of all, this trinomial, all terms are on one side, great. The other thing I want to look for is my x squared term positive? I always just like to have it in that order where x squared is positive, and then it doesn't matter the other two, but I like to have it where it's all on one side where the x squared is positive. Now, what is the coefficient of x squared? It's actually 1. So our a value is equal to 1, our b value is equal to -4, and our c value is equal to +1. As you can tell, I took the sign that is out front of the b term. The sign goes with it, and that goes for a, c, anything. It goes for all three of these. If the sign is negative, you treat it as a negative. If it's positive, you treat it as a positive number. All right, now let's plug it into the quadratic formula. X is equal to -b. Our b value was -4. The negative that's already there is just there in the equation by our derivation, plus minus the square root of b squared, which is -4, and I'm going to put it in brackets as such. So it's going to be -4, close the bracket, squared, minus 4, a was 1, c was 1, divided by 2 times the a value, which was 1. Now, continuing this below, it's x is equal to -4 is 4, or negative times a negative is a positive, plus or minus the square root of, well, -4 squared is 16. 16 minus 4 times 1 times 1, that's just -4. This is going to give us 12 all over 2 times 1, which is 2. Now, for some of you, you might be tempted to just stop here and be like, that's good. No, we got to reduce this radical. And this is a Math 10C skill. What is the largest perfect square that divides this 12? It's actually 4. So I could rewrite the radical as 4 times 3, all divided by 2. What happens when I take the square root of 4? It gives me 4 plus or minus 2 square root 3 all over 2. And then here's where I call the all or nothing principle. You must divide all three. If all three of the coefficients of this do not divide, then none of them divide. So let's just do a quick survey. 4, 2, and 2. Are they all divisible by a number? Yes, and that number is 2. Therefore, your solution to this is going to be where x is equal to 4 divided by 2 is 2, plus or minus 2 divided by 2 is 1. And so this is going to give us 1 root 3. Now, would we really need the 1 in actuality? No. So if you just wrote it as 2 plus or minus square root of 3, that is totally fine for me. In fact, that is probably encouraged. There's your solutions. You could separate them, you could not separate them. I think it's fine like this. This is a valid solution type. As long as you highlight it all together like this, I will totally accept this solution. In fact, it is a very appropriate solution in terms of the mathematics of this. All right, let's go on to example B here. In example B, the first thing we got to do is make sure all terms are on one side and the x squared is positive. X squared is positive here, so I'm going to add 10 to both sides, starting by moving that term from the right to the left. Now this is going to give me 3x squared plus 11x plus 10 is equal to 0. Now I'm going to write this as a is equal to 3, b is equal to positive 11, and c is equal to 10. It's really important that we identify all of them to start the problem. Now, once we identify them, we go into our equation. X is equal to negative, which is already there in the equation, b, which goes in brackets, plus or minus the square root of 11 squared, which is the b value, minus 4, a, which is 3, c, which is 10, all divided by 2 times a, which is 2 times 3. Now, continuing this below, we're going to get x is equal to negative 11 plus or minus the square root of, well, in your calculators, we could do this all together, or we could put the values separate, but maybe we actually just do a step where we write them. The square of 11 squared is 121. 4 times 3 times 10, that's 12 times 10 is negative 120, all divided by 2 times 3, which is 6. Now what I'm going to do is write this as x is equal to negative 11 plus or minus the square root of 1 divided by 6. Now, because this one actually works out pretty nicely in terms of an integer value, or a rational number in general, we're actually going to solve this. The square root of 1 is 1, and so I'm going to write this as this. X is equal to negative 11 plus or minus 1 over 6. Now, let's do the two different cases. Starting with the first case, x is equal to negative 11 plus 1, all divided by 6. This is equal to negative 10 over 6, which is equal to negative 5 over 3 as a reduced fraction. Our second x value is going to be x is equal to negative 11 minus 1 all over 6, which is the same as negative 12 over 6, which is equal to negative 2. There's our two solutions here, and we could highlight them. Now, if you just highlight the x is equal to negative 5 over 3 and x is equal to negative 2, great. I just like to highlight all the work here, showing that there is a form being followed. We're reducing our fractions if possible, and we're getting our final solution in the most simplified form. Okay, let's continue moving forward. I look at this example here. Now, anytime you have a decimal, really easy way to get rid of these is you multiply by either 10 or 100, depending on how many decimals you need to get rid of. So if we need to get rid of one decimal, multiply it by 10. If we need to get rid of two decimals, multiply it by 100, and that will move the decimal spot that 1 or 2 times you need. So in this situation, to make our numbers all nice, I'm going to multiply both sides by 10, because if it's only one decimal spot I need to get rid of, let's multiply it. Now, you could solve this with decimals, but I would highly encourage just make them into integer values. Now, what we're going to do is we're going to make this 10 times 0.1 is 1, which is equal to 10 times negative 2.2 is negative 22x squared. Negative 2.4 times 10 is negative 24x. Now what I'm going to do is I'm going to take these from this side and add them across. So this should be plus 22x squared plus 24x. And if I do that to both sides, then it's going to give me the following trinomial. I'm going to have 22x squared plus 24x plus 1 is all equal to 0. Now we can identify our a, b's, and c's. A is equal to 22. B is equal to 24, or the coefficient of x. And then c is our constant. That's a really easy one to remember. C is always the constant value. So C constant, just whatever it begins with, you can easily tie it to that letter. Now from here, we're going to plug it into the quadratic formula. X is equal to negative 24. Remember that negative that goes out front here, it's already in the quadratic formula by derivation, plus minus the square root of, we're going to take the b value and square it, 24 squared, minus 4 times a, which is 22, c, which is 1, all divided by 2 times the a value, which is 22. All right, this is going to give us x is equal to negative 24 plus or minus the square root of, let's see if we can get a specific value out of here. In our calculators, you should be getting 488. Now, from this one, we can actually separate this, and I should do my denominator before I actually continue forward. So 2 times 22 is 44. All right, now we want to reduce this radical or make it in its most simplified mixed radical form. When I do that, I'm going to get x is equal to negative 24. The largest perfect square that divides this one, you could try it out, maybe prove me wrong if this is not the solution, but it seems fine to me. When I take 4 and I multiply it to 122, this gives me the most simplified radical. I can't divide 122 anymore such that there's another perfect square in there. I divide this all by 44. I take this one step further and it's negative 24 plus or minus, the square root of 4 is 2. I leave behind the 122 because I can't perfectly square root that number, divide it by 44. Now, here's where the all or nothing principle comes in. 24 and 44, 2 and 44. They all have to divide by a common number. In fact, that common number is 2. If I divide all of these by 2, then it works. So let's arrow off to here and do our solution. Therefore, x is equal to 24 divided by 2 is negative 12. 2 divided by 2 is just 1, so I'm just going to leave that out. I'm just going to write my square root of 122, because you could put a 1 in front, but I mean, not really a point. And then 44 divided by 2 is going to give us 22. There is your solution. I can't reduce this anymore, especially if I want to keep this as the most simplified form that is a rational number in this case. Well, maybe not so much rational, but if I want to simplify this in its exact form, as they call it, exact form means we don't want to have any sort of decimals floating around. We don't want it to make it to like the nearest 10th or the 100th. They might ask that in a problem, but not in this one. Okay, now let's go up to example D. Example D might look really difficult on surface value, but it's actually not. Just requires a little bit of expansion and then collection of terms onto one side. So if you're ever given something like this, let's take this and first of all, expand it. 2d times d is 2d squared. 2d times negative 2 is negative 4d. 3D is positive 3D. 3 times negative 2 is negative 6, is equal to, on the other side, d times d is d squared. D times negative 3 is negative 3d. 9 times d is 9d. And then 9 times negative 3 is negative 27. And then we had that positive 16 that was just kind of floating on the outside. Now, let's collect the like terms on both sides. First and foremost, there's no common d squared on the left, so I'm going to leave it as that. Negative 4 minus or plus 3 is negative d. Minus 6 is equal to, on my right-hand side, there's only 1d squared. Negative 3 plus 9d is going to give us positive 6d. And then 27 plus 16, this is going to give us negative 11. Perfect. There we go. All right, now I want to keep that d squared term positive. So if d squared is to be positive, well, there's 2 over here and there's 1 here. So what I'm going to do is I'm going to take all of the right stuff and move it over onto the left-hand side. So let's take all of this and subtract it over. This is going to be negative 2d squared minus 6d plus 11. And by doing that, we're going to move it over to our left-hand side. 2d minus d squared is d squared. Negative d minus 6d is negative 7d, and then negative 6 plus 11 gives me positive 5, which is equal to 0 now, because we've moved everything from the right-hand side. Now let's identify our a, b's, and c's. A is equal to 1, because technically the coefficient on this d squared is 1. Then we go on to our c value. C is equal to negative 7. Not C, sorry, B value is equal to negative 7. C value, which is over here, is going to be equal to our positive 5. Now we're going to plug this into quad formula. We're going to write this as x squared, or x is equal to the negative b, which is negative 7, plus or minus the negative 7 squared, which is our b value, minus 4a, which is 1, c, which is 5, all divided by 2 times a, which is 1. Now let's do a little bit of work with this. X is equal to negative negative. Negative times negative is a positive 7, plus or minus the square root of 7 squared is 49. 49 minus 20 gives us 29 under the bracket. And I probably don't need that long of a radical. There we go, all divided by 2. Now, what I want you looking for is, can you simplify this radical? Once you get it to this stage, we want to simplify it as much as we can. 29 is actually a prime number. So all it can divide by is 1 in itself. So I could write it as 29 and 1, meaning I can't do anything with this radical. In fact, this is the solution right here. So that's always possible. And in fact, if the numbers actually worked out to this, they might even ask you to convert it to a decimal. But for this case, this is good enough. If that number in the radical is prime, or the radicand position, which is that position under the radical, is a prime number, then we just have to leave it. All right. Now, let's move forward into our application problems. So the application problems are the ones that are going to get us to do a little bit of setup in terms of like maybe taking a visual and taking some pieces from the sentence and then putting it into a visual, which will then help us solve this. In the case of this one, here's what they ask us to do. A picture measures 30 by 21, and we want to crop the picture by removing the same amount from the width and the length of the picture. This is going to reduce the overall area of that picture by 40% of the original area. Determine the width of those strips removed in order to make this 40% of the original area. All right, let's draw a picture here, because like without the picture, I think this is sometimes tough to visualize. So just draw some sort of rectangular picture like this, and we're going to label the outside as, our longer side will be 30. We'll make, and I'm going to put it as 30 centimeters, and I'll even zoom in here. So this is going to be 30 centimeters. And then I'm going to make the width here 21 centimeters. And then they told us, well, we're going to remove the same amount from both sections. So what I'm going to do is I'm just going to draw a horizontal line on the top, draw a vertical line on the side here. And then what I want you to do is I just want you to shade that in. So we're going to shade it all, indicating that this is the area that is being removed or cut out in order to reduce our picture size, because we're trying to crop this picture. Now, what we're going to call these is, these strips are going to be a width of x. It's x and x. If I remove out x width from our length and x width from our actual width, what this is going to do is reduce it, but now we need to describe these internal dimensions. So if I remove out the x and make this new dimension here, and let's make sure I just backpedal that so it's a neater arrow, this means I'm going to be taking that 21, which was the original width, and subtracting away this x that represents the strip I'm removing from that width. So we're going to write it as 21 minus x is the new dimension. And we could even write that in here as well. 21 minus x, representing that that is that new internal width. Now, the one that's we're going to put down here, which I'm going to arrow to, which is here, our new length is going to be, well, it's 30, which was the original, minus the x that we remove, because that x is that strip here, and so it's being removed off of the length here. We want to take that away. I could write this as 30 minus x on the interior, representing that piece there. Now, I even want to just highlight these just to make them a little more clear too. Not that I have to, but there's that new width. There's the new length right there, just to show you that this is the area that we're solving for, and these are the new dimensions that that represents. Now, we're going to put this together in an equation here. So off on the side here, what we're going to do is we're going to write out the original area, which was 30 multiplied by 21, but it's not 30 times 21 that we're trying to get to. It's the new area, which is 40% of that original area. When we write this as a decimal, remember from our previous grades, 0.40, this is the same as 40 over 100, which is representative of 40% as a decimal. And so if you ever see that, anytime we talk about percentages in mathematics, we always put them as decimals into our numbers. And then if we're actually answering the question in terms of the context later on in a sentence, I mean, you could say 40%, but we always want to use the decimals to represent that it is a fractional amount out of a whole amount, or it's 0.4 out of a total 1. Now, this is 40% of the area, which is then equal to those dimensions that make the new area. So we're going to say this is 21 minus x, which is the width, times the length, which is 30 minus x. All right, let's expand both sides here. 30 times 21 times 0.4 is 252, which is equal to, on my other side, 21 times 30 is equal to 630. 21 times x is negative 21x. Negative 30x is our negative next number. And then we're going to take the negative x and negative x, which will give us positive x squared. Collecting the like terms, we're going to write this as 252 is equal to 630. Negative 21 and negative 30 give us negative 51x plus x squared. Now, we want to move all the terms onto one side. To do that, our x squared is positive on the right, so let's keep it there. I'm going to subtract 252 from both sides. So if I minus 252 from both sides, I'm going to get 0 is equal to x squared in descending order minus 51x. 630 minus 252 gives me positive 378. All right, now we have an a, b, and c. A is equal to 1 because 1 is the coefficient on x squared. Our b value is equal to negative 51. Our c value is our constant, which is 378. Awesome. Okay, from here, we're going to plug this into our quadratic formula. X is equal to the negative 51 plus or minus the square root of the b value, which is negative 51 squared, minus 4 times a, which is 1, c, which is 378, all divided by 2 times a, which in this case is 1. Now we're going to go down here and write negative is positive 51, plus or minus the square root of, when we plug these into our calculator, 51 squared minus 4 times 378, it actually gives us 1089, all divided by the 2. Now what we're going to do is simplify this, and we're going to get 51 plus or minus. The beautiful thing about this in your calculator, the square root of 1089 is actually equal to 33, all over 2. Now you're probably thinking, okay, wait a minute. So now we're getting exact values in terms of an integer value, not as a radical. Why did this one work out that it was a perfect square? Anytime you have something dealing with like length and width, just assume that we're going to pick numbers that will always be nice and a radical that will simplify to an integer value. That's very, very common because more often than not, we don't want to give you numbers that would turn into decimals unless that was specified in the solution somewhere. But most of the time we want it to be an integer value that comes out of this x here because it's a reflection on how much we're altering this picture by. And if we start introducing decimals, it can sometimes be tough, but I mean, it could happen. I don't want to say it would never happen, but it's just more rare. Now we want to generate our two scenarios here. First and foremost, we're going to get one scenario, which is 51 plus 33, all divided by 2, which is the same as saying 51 plus 33 is 84, divided by 2, which is equal to 42. So one possible x is 42. The other one is x is equal to 51 minus 33, all over 2, which is equal to 51 minus 33 is 18 over 2, which is equal to 9. Now we want to look at this and be like, okay, if one of our solutions was 42, the other solution was 9, which one makes sense to use? Now let's zoom out on this problem because one of these can be determined as extraneous. Extraneous, remember, it does not satisfy the given solution or does not satisfy the given equation or scenario. We zoom up to here. If I take 21 and I subtract 44, or 42 in this case, 21 minus 42, this is a negative number. We don't want that. 30 minus 42, this is also equal to a negative value. And should we have a negative length and width? No. And so we got to be very careful with this. If it does not suit the context of the problem, what I want you to do is I want you to circle it, put a line through it, and write ext, meaning this is an extraneous solution. It is beyond the scope of the context of this problem. That means the x value, or this width of the line here, or the width of the section we take out, is actually equal to 9. It is our other solution. So we want to write a quick sentence for this, maybe below our diagram. We're going to say, therefore, the width of the strip and it's the width of the strip removed is 9 centimeters. There's your solution. That's what you can highlight. That's what you can use. Perfect. So just keep an eye out for those extraneous solutions because they do pop up, and they're one of those things that can definitely catch you off guard if you're not looking for them. All right, example 3, very similar type of problem, just slightly different. We have a rectangular piece of tin, 50 by 40, that's made into a lidless box with a base area of 875 by cutting squares out of the corners in order to fold them up and bending up the sides. Determine the side length of each square removed. Okay, determine the side length of each removed square, I should say. All right, now let's draw out a visual for this one because it's a little bit tough if you're more of a visual person. I know for sure I am. When I draw this out, I'm going to draw just the larger box and the larger net of this box. There it is. Now, what we want to draw on the inside is the following. I would like you to draw an internal box here, and actually, you know what we're going to do is I'm just going to have you sketch this into your diagram. I want you to do a dotted line across the top here. I want you to do a dotted line on the bottom. I want you to do a dotted line towards the left-hand side, and I want you to do a dotted line on the right-hand side. Now, I want you to sketch in the following. We know they told us that the base of this box, when we cut it out and then we fold it up, the base area was equal to 875. I want you to write in 875 right here. This is the 875 centimeters squared. It's that internal side here. And what we're actually going to do is we're even going to box this in black, representing that this is that base area they're talking about. What areas are they talking about that are cut out? It's these ones off to the side. It's the x times x. The part that we're going to remove from all these boxes is these corners here, because if we remove these, then we can fold up these edges. And when we fold up these edges, we'll get the nice box here. So you can think about it as these parts that are in red here, they're going to be removed. And then all of these sides that I'm just shading in right now, these are going to be folded up to make the sides of the boxes, which is very common. You have to make these little slits in order to fold it up. And you could even use your hands in a way to create an L shape and then fold them up so that your edges of your hands meet. You would easily be able to see, oh, that's exactly how these boxes come together. Now, we need to figure out what this x value is. So what we're going to do in this situation is we need to set up an equation that revolves around this. So first and foremost, when we want to solve for these internal pieces here, or this here and this here, our internal length and width that make up this box here, what we must do is, and I'm actually going to arrow these back just a tad, so I'm going to cut these back and then go, we're actually talking about here and here, even though those are the same thing. If we know that the overall piece of this was 40, so the entire thing along the bottom was 40, and maybe this is why I'll even go back on these blue arrows, we should probably put in our original dimensions first and foremost. Our original dimensions were 50 by 40. It's not really going to matter where we put them, but maybe I put 50 here and then 40 here. 50 and 40. Now, in order to determine these internal lengths and widths that are the new lengths and widths, we're going to arrow into here and go, well, if it's 50 for the entire piece end to end, and there's an x that's here and an x that's here, in order to get this piece that's right here, we're going to take the original 50 and minus those two x's. So 50 minus 2x. Okay, in order to get the internal piece that's here, what we're going to do is say, well, if this is 40 for the entire side, and we have an x here and an x here, and we want to only get this piece, we're going to take 40 and minus the two x's that are on the endpoints. Okay, so now we have a dimension for the length and width given this box where we cut out these x's. So now what we need to do is generate an equation that separates or puts this all together. Our base value, or the area of the base, is 875, which is supposedly, and let's make sure I put it as 875, not 857, 875 is equal to get the area of 875, we multiply these two dimensions in blue. It's the length times the width. So 40 minus 2x times 50 minus 2x, 40 minus 2x, 50 minus 2x. It really doesn't matter which one you put first either, so just be aware of that. Now, when we expand this out, we're going to get 875, which stays the same for now. 40 times 50 is going to give us 2,000. 40 times 2 is going to give us negative 80x. 2 times 50 is going to give us negative 100x. And then negative 2 times negative 2x is going to give us positive 4x squared. Now, from here, what we're going to do is we're going to write this as, we want to collect the like terms and then put everything to one side. I'm just going to keep 875 on the left for now. 2,000 minus, this is going to be negative 180x plus 4x squared. Now what I'm going to do is I'm going to subtract this 875 from both sides. Minus 875, minus 875, because I want to keep the x squared term positive that's on the right here. This is going to give me 0 is equal to 4x squared minus 180x, and then 2,000 minus the 875 is equal to negative 1125, 1,125. Okay, here's where we want to go into our quad formula. So we're going to identify the a's, b's, and c's. A is equal to 4, b is equal to negative 180, and c is equal to 1,125. It's the constant value. Therefore, x is equal to the negative 180, which is our b value, my apologies, plus or minus. So we go plus or minus the square root of negative 180 all squared, minus 4 times the a value is 4, the c value is 1,125. We're going to divide this all by the a value, which is 2 times 4. This will give us x is equal to positive 180 plus or minus the square root of. In your calculator, if you do this piece here, we end up getting that it is 120 actually. So it works out as a nice perfect square. So I'm actually just going to even write the number itself. I mean, I could write the radical in the simplified radical, but the simplified radical would be the 180 squared minus 4 times the 1,125. This simplifies to 120 when you square root it, all divided by 8. Now, I realize that these can both be divisible by 8, which is kind of nice, but in this situation, they've actually asked us to figure out what these dimensions are, given that these x values are cut out. So what we're going to do is we could reduce them all by some factor, or we could just simply put them into our calculators at this point, because we want to figure out what are these two independent pieces here. Now, just for the curiosity of it, what I'm actually going to do is let's actually reduce it, because I do want to show that as an example here. If I reduce both of these, let's do that here. 180, if we divide it by 8, we're going to get a decimal, so we don't want to do that. Maybe we take 180 and divide it by 4. This gives us 45. So then we could do 45. If we divide 120 by 4, this is going to give us 30. And then if we divide 8 by 4, it's going to give us the 2. There we go. So now this is as a reduced fraction, or everything being reduced by the all or nothing principle. Now what we can do is we can get our specific x values from here. Because 2 is a prime number, I can't go any further with this. So what I'm going to do is maybe, let's do it below here. So we're going to do x is equal to, for first case scenario, x is equal to 45 plus the 30, and we'll actually make sure we write this out. 45 plus 30 all over 2. This is going to be equal to, and I'm going to give it as a decimal, 45 plus 30 divided by 2 is 37.5. All right, and then my other x value, which I'm going to branch down here, x is equal to 45 minus 30, because it's the plus minus of that radical from above. When we take this, it's 15 divided by 2. 15 divided by 2 is 7.5. And so when we look at this, now we have to do what we did in our previous problem. We need to see if one of these values is extraneous based on the situation of the problem. I go back up to the situation. If I put an example of 37.5 into x, well, that's going to make this negative. 40 minus 2 times 37.5, that's a negative number. Same thing here. 50 minus 2 times the 37.5, that's also a negative value, meaning the 37 is extraneous. The x value that we're looking for, or the amount that is cut out from the corners in terms of a width is 7.5 centimeters. The other one, what we want to do is we want to circle it, cross it out, write extraneous above it. And it's really important you do this, because if you leave both solutions and you just highlight both and say, hey, these are my x values, you've ignored the fact that 37.5 cannot exist in this problem. And in fact, it's an extraneous root. All right, we're going to make sure we write a sentence just below here. So just like we did in the previous one, right below our diagram, therefore the width of the cutout is 7.5 centimeters. There we go. And it really doesn't matter where you put the sentence, just as long as there is a sentence in terms of these application problems, because you do want to explain your context. And if you just jump right to the solution, you highlight the x equals 2.5 or 7.5, and you just call it quits there, it's like, okay, 7.5 what? Did you need to bring it back up into the situation? Is 7.5 a solution to a specific part of this? Just make sure there's a short sentence in there so that it's very clear. Now, in part B, they actually to do something really simple here, and that's determine the volume of the box. To determine the volume of the box, volume is always equal to area of the base, which is often written as capital A, times the overall height. Now, the height of the box is actually the amount that we cut out. If we fold up the box, the height of each of these walls is x. So what we're going to do is we're going to multiply the area of the base, which is 875, times that part that we just did, which is the width of the cutout, 7.5, that's going to give us the volume, and we'll include our units. Area is 875 centimeters squared multiplied by the 7.5 centimeters, which represents the height of the box when folded up. We get a volume equal to, and we'll maybe round it to like one decimal place. This is going to be 6,562.5 centimeters cubed. There we go. And as you can see from previous lessons, or previous even years, not previous lessons, but when we even talked about measurement in Math 10C, we would have looked at this and said a centimeter squared plus a centimeters, that will be centimeters to the 1 power, centimeters squared. You add their exponents, you get centimeters cubed. Hopefully this isn't too much of a surprise for you. And you can even think about it as it's a length times width times height. That's 3 dimensions multiplied together. That gives you volume of the 3-dimensional object. All right, now we're going to move forward into part 2. Part 2 is determining the nature of roots, or classifying how many roots there are based on the quadratic formula. And there's a really important piece of this. When we look at the quadratic formula, I want you to look at something in particular. It is the discriminant. The discriminant is what we're going to call this piece that's the b squared minus 4ac. It's the part that makes up the radical. The part that makes up the radical can actually tell us, is there 0 roots or no real roots? Is there one root, one real and equal root, or is there two distinct real roots? And this is the power of the discriminant. You'll probably see questions like this. Let's just go through an example of each of them and just provide some like rough numbers of what this could look like. So the discriminant, b squared minus 4ac, all under the radical. The part under the radical can discriminate between the 3 different types of solutions. So if you want to highlight that as well, when we look at this, discriminates between the 3 different types of solutions. In the first situation, if the discriminant is greater than 0, another way to say greater than 0, if you want to throw this in your notes, is actually that it's positive. If the solution is positive for the discriminant, there is 2 distinct real roots. And so we're going to look at this and be like, suppose we have the example to our just below here. Let's say that this is equal to x is equal to 1, this one is x is equal to 4. Our equation to symbolize this would be x minus 1, and then x minus 4 is equal to 0. 2 distinct real roots. They're independent of one another. They are connected to the same equation, of course, but they are independent of each other in terms of different solutions. The other situation is, instead of greater than 0, we could have where it's equal to 0. If the discriminant's equal to 0, I just want to point something out before we actually classify it. When this is equal to 0, it wipes out the whole radical, and the only solution is b over the 2a. So that is one solution, which goes exactly into the point. We're going to get 2 equal and real roots, or aka there is one x-intercept when it's equal to 0. Let's say that this is like x is equal to 2. Our equation would look like the following, i.e. it would be x minus 2 times x minus 2. We know from our perfect square trinomials, or our factors that ended up being the same, we can combine them into one binomial and square it. This is an example where if we have a perfect square trinomial, it is 1 equal they say 2 equal because it's two factors like this, x minus 2, x minus 2, but I like to say it's one root that is one real root, but technically it's 2 equal because by the factors there is two separate factors. Okay, lastly, we go into the situation where if we've had two real and equal, which is when it's equal to 0, where it was greater than 0, we said that that was two distinct real roots. Now we're going to talk about if the number is less than 0. Again, less than 0 is just a fancy way of saying that the number is negative. If the discriminant is negative, it will float above. It never crosses the x-axis. And so if it never crosses the x-axis, we classify this as having non-real roots or no real roots. And moving forward, you would actually say there's two imaginary roots, but we don't introduce the complex plane until like well into university, probably second year mathematics, and some of you might not even get there. So even bringing that up is sometimes a tough topic, but just know that in this situation, we're going to say non-real roots because we only deal in the real plane specifically within our mathematics at the high school level. All right. Now, an example of this one, I mean, we could put together a quadratic that might give this. For example, maybe you have like something like 3 x minus 1 squared plus 4. And this would be equal to 0 as an equation. This is an example of something that would give you a graph that's shifted above. As we know from quadratic functions, this would exist somewhere above. It's not symbolic of the one on the right, but I mean, it does the trick. Actually pretty close, not bad. All right, now let's look at the following, and based on the situation of what they describe in terms of giving us certain x values, what are the nature of the roots? The nature of the roots is just a fancy way of saying how many solutions are there? Is there no real solutions, two real and equal solutions, or two distinct solutions? In the first situation, we have an x equals 3, x equals negative 4. Those are two distinct solutions. Therefore, there is two distinct and real solutions. Or you could even say zeros. Two distinct real zeros. All right, now in our next piece here, we go on to x equals plus or minus 2 root 5. Well, if it's plus or minus the value, plus or minus means there's two separate solutions, the positive and the negative. So again, we're going to say it is two distinct real zeros. Awesome. Okay, we go into part C. We're only given x equals 6. That means that there is two equal but real roots. There we go. So it only crosses the x-axis one time. That's what it means when x equals 6. All right, we go down to part D. We see that is negative 3 plus or minus the square root of 5 over 2. This is, well, because of the plus minus being there and the radical being a real number, in this case it is part of the real plane, we're going to say that there is two distinct and real roots. Awesome. Lastly, we go into part E. Part E, you need to be aware of something. If I take the square root of a negative value, aka our discriminant, the part that's under the radical is negative, that means that this leads to non-real solutions. This cannot happen. I'm going to even arrow and say that. This cannot happen, at least for now. If we take a square root of a negative value, this means that there is no real solutions or no real zeros, which is another way of saying there are no solutions. Because remember in this unit that there's so many synonyms for the zeros, x-intercepts, roots, or zeros. I mean, or solutions, zeros, roots, or x-intercepts. All of those are synonymous to each other. So it's really hard when they start throwing around all these different terms and making it all formal. But if you say there's no real zeros, perfect, full marks. If you tie that together with no solutions, even better. Because realistically, for now, until we get to the complex plane, we're going to call it no solutions or no real solutions. All right. And maybe that's what I'll put here, just to be a little technical about it. I'll say no real solutions. Awesome. Okay, let's move forward here. State the nature of the roots, aka how many x-intercepts there are, based on the given information here. And for these ones, we want to use the quadratic equation such that we're using the discriminant to help us out here. And so when we look at this piece here, we see that we have an example like 9x squared minus 30x is equal to negative 25. First and foremost, let's make sure we add 25 to both sides because we want all the terms to be on one side and we want our x squared to be positive. So this is going to give us 9x squared minus 30x plus 25 is equal to 0. Now from here, we're going to do our discriminant. Discriminant was equal to b squared, which is negative 30, all squared, minus 4 times a, which is 9, b, which is 25. There we go. Now, this is going to give us a value of, when we put this into our calculator, we actually end up getting 0. And so if the discriminant is 0, we knew that this was our case where the overall term had two equal and real solutions. I know sometimes saying two equal and real, it's a little confusing because you're like two, but if it's the same value, why do we call it two solutions? It's just because when you factor it, you're going to get two factors, but they both lead to the same solution. So for this one, we're going to say two equal and real roots. It's really important you put the real roots because if we have it less than 0, I mean, we have imaginary roots, so we want to make sure we have this as real roots. Okay, we go into part B. They're all on the same side, which is great. We're going to label our A, B's, and C's. We have an A value equal to 2, a B value which is equal to 3, a C value which is equal to 5. Plugging into the discriminant, we get a B, which is 3 squared, minus 4, A, which is 2, C, which is 5. This is 9 minus 4 times 2, which is 8, times 5, which is 40. We actually end up getting a value for the discriminant where it's equal to negative 31, which is less than 0. If our discriminant is less than 0, it means we have the following. We have two, and we're just going to say non-real roots because I don't want to throw us off here. Non-real roots or non-real solutions. And in some math courses or some 20-1 courses, you would also see them say two imaginary roots or two non-real roots. That's also acceptable. So if you write two non-real roots, I will totally accept that. But if you want to just boil it down to there's no real roots, that's perfect for me. Now, when we go over to example C, this one's just going to require a bit of expansion, moving some terms. I'm going to multiply the 4 in, giving us 4x squared minus 20x plus 20 is equal to negative 5. I'm going to add the 5 to both sides, so plus 5 and plus 5. This is going to give me 4x squared minus 20x plus 25 is equal to 0. Now, our A, B, and C, A is equal to 4, B is equal to negative 20, C is equal to 25. Now, from here, we're going to plug this into our discriminant. Discriminant is the negative b squared, or in this case, the negative 20 squared, minus 4 times the A value, which was 4, C value, which is 25. When you plug this into your calculator, we're going to get D is equal to, and I ended up getting 0 in my calculator. From here, if we get that it's 0, we know that there is two real and equal roots, or two equal and real roots. Perfect. So unfortunately, we didn't see two distinct and real roots, but no problem. It's just the byproduct of what's happened in terms of the numbers. So we just want to be very careful with those. Now, let's go into example 3. Determine the values of m such that this quadratic equation has two distinct and real roots, no real roots, and then for this one, it doesn't look like they want us to look for where there's the 0 case or where they're both equal. So for this situation, we're going to write it in the following way. Well, first and foremost, I want to take this equation here, this piece here, and I want to solve it such that everything is on one side where the x squared term is positive. So I'm going to rewrite that, and I'm just going to rewrite it actually in the middle here. I'll underline it and then arrow over and continue right here. This is going to be mx squared plus 4x minus 3 is equal to 0. And I'm just going to make that a touch neater. Mx squared plus 4x minus 3 is equal to 0. That's me rewriting the equation with all the terms on one side. Now, we're going to label our A. A is equal to m, B is equal to 4, and C is equal to negative 3. Our constant is the negative 3. Now, to be two distinct and real roots, it must be that the discriminant is greater than 0. We've discussed that on the previous page. So I'm going to write this first and foremost as discriminant is b squared minus 4ac must be greater than 0. Now what I'm going to do is I'm going to plug in the b, a, and c. So my b value was 4 squared minus 4 times the a value, which is an arbitrary m. times the c value, which is negative 3, must be greater than or equal to 0, not equal, but just strictly greater than 0. In this case, when we solve, we're going to talk about it being strictly, because if it's equal, we know it has two equal roots, so it must be strictly greater than. I'm going to go 16 minus negative 4 times positive 3. This actually ends up positive, so I'm going to write it as positive 12. M is greater than 0. Now what we can do is we can move this 12 across. So I'm going to move 12 and move 12m. Some of you might be like, hey, I'll move 16, but I want to move 12 intentionally to show you what happens with the sign here. 16 is greater than or equal to, not greater than or equal to, but just strictly greater than. I always don't want to make sure that I slip that up on there. Now, we're going to take our negative 12, we move it across. If we divide by negative 12 here, which we're going to do, because we want to isolate this m value and figure out what that m is, when you divide by a negative, it flips the inequality. If this was originally faced in this direction, it is now going to flip the opposite way when you divide by a negative. It's really, really important you see this. So 16 divided by 12 as a reduced fraction, this is going to give me 4 over 3 as a negative value. If the inequality was facing open towards this 4 over 3, when we divide by the negative, it now flips the other way. It will be m must be greater than the negative 4 over 3. We flip it when we divide by the negative. That's intentionally why I showed you this method. It's only when you divide by negatives that you flip it. And I'll make sure I even underline this here. Here to here. Why did we change this? And I'll even put a little square bracket here. We said that if we divide by a negative value, the inequality flips from this to this. There we go. And I don't know if that's going to make it any clearer, but there you go. And then I'm just going to finally write this as m is greater than 4 over 3 negative. And all I did was just flip it from left to right. That's it. So I didn't do anything fancy with like changing the sign again or doing anything complicated like that. We just changed the order. M is on the left, the negative 4 over 3 on the right. There you go. Perfect. All right, let's go to where we have the discriminant such that it will give us no real roots. Now, to have no real roots, we need a discriminant that is where it is actually less than 0. And so we're going to go discriminant is equal to b squared minus 4ac, which is less than 0. Let's start plugging in the values. The b value was 4. The a value was the arbitrary m. C value was negative 3. Must be less than 0. This is 16 plus 12m is less than 0. Now, for this example, I'm just going to move the 16 across because it really doesn't matter which one you move across. This might actually save you a bit of a headache of flipping the sign when you divide by the negative. This will give us 12m is less than the negative 16 on the other side. We divide both sides by 12. And we already know this reduced fraction, m is less than negative 4 over 3. Now, here's something I want to find that is very interesting about this. When you compare the two here, you zoom out. All of the work is the exact same. I want you to realize that. All of the work in terms of the algebra is the exact same. It's the direction of the inequality that changed. Do you see how when we had two distinct real roots, in this specific situation, m must be greater than or equal, or not greater than or equal to, but strictly greater than the negative 4 over 3. When it was no real roots, it just flipped the other way. So to have two real roots, it must be this. To have two non-real roots, it must be the other way. Now, we can't guarantee that the inequality will always be greater than for two distinct and less than for the non-real. So don't make that broad assumption that you just have the inequality right away. You still need to solve for it, but just know that if you can solve for one, then it automatically tells you about the other. So you must at least solve for one in order to get the other piece, as is my kind of summary of that point. Now, if I wanted to add a part C here that said, instead of it being two distinct and non-real roots, what if I wanted to have equal roots? What I would do is take this, and I'll even maybe write this in the bubble, therefore, two equal real roots. This would mean that m is equal to negative 4 over 3. Because we knew that all that would change about this is if the inequality faces one way and then it faces the other, from two distinct real roots to non-real roots, and then when we have the equal case, it was one root, that means we wanted to eliminate our radical. When m is equal to negative 4 over 3, it will eliminate the radical term and make it 0. Now, that's a secondary tangent to this. So, I mean, you could include that, you could not include that, totally up to you, but I found it kind of interesting about this problem. All right, going into example 4, for what values of k will this trinomial give you two equal roots? Two equal roots. This was that missing case above when we have two equal roots, and I want you to underline this in your notes. Two equal roots. This means that the discriminant is equal to 0. Anytime they give you that piece of information or they give you a classification of the nature of the roots, as they call it, the nature of the roots for this trinomial is supposedly where we have two equal roots. Two equal roots is where the discriminant is 0. Now what we want to do is plug in our a, b's, and c's. We just got to point them out. First and foremost, our a is our 16. It's the coefficient of the x squared term. Our b value is equal to negative k. It's the arbitrary k value. And c is the constant, 25. Now, we want the discriminant, which is equal to b squared minus 4ac, to be equal to 0, because we're looking for where it's two equal roots. Now, from here, we're going to plug in our b value, which is negative k all squared minus 4 times the a value, which is 16, times the c value, which is 25, is equal to 0. This is going to give us where we have on this piece, negative k squared is k squared, minus 4 times 16 times 25 is negative 1600, which is equal to 0. I'm going to add the 1600 to both sides, plus 1600 plus 1600. This is going to give us k squared is equal to 1600. Now I must square root the value here. So I'm going to square root k, square root the 1600. This gives us k is equal to, remember from earlier in our unit, a square root gives us a plus and minus case. So it's going to be plus and minus 40 as the value. And then therefore, that's the two solutions such that we get two equal real roots. That's what would satisfy this. So if I put 40 in for k, and I could even do that above here, if I wrote this as negative 40 or even a positive 40 here for k, both of these would satisfy this in terms of giving us those two equal roots where it crosses the x-axis one time. All right, now let's flip the page here. We're going to look at some more application problems. These application problems are just going to have us look further into this idea of if we want to look at this methodology around the completing the square or factoring or doing some sort of application using these three algebraic methods we've learned up until this point, this final example gets us to do a close examination on all this. So we've actually seen this in a show, or hopefully you've seen this in a show, or some sort of homework question before. This is actually a textbook problem. The A1 Sporting Goods store sells 90 ski jackets in a season for $200 each. Each $10 decrease in the price will lead to 5 more jackets being sold. Write a quadratic function to represent the revenue if x is the number of $10 decreases in price. So they've actually defined x for us in the problem. That might be something important to highlight just so that we can go back to this eventually. All right, now in this problem, what I always recommended from our quadratic functions unit is highlight the quantity information and then highlight the other piece of the quantity information. So if 90 jackets are originally sold, how many jackets are either lost or sold as an addition from the original? We're then going to look at the price. The price was 200 originally, and what happens? There's a $10 increase, or a $10 decrease, I should say, for every additional amount of jackets that are sold. So that's our price statement. Now we're going to put this together in terms of a revenue statement. It's going to be revenue is equal to the price times the quantity price times the quantity. In the first bracket, we're going to write this as they originally sell for 200, but then they are telling that there might be a $10 decrease. We don't know how many decreases, so we're going to put an arbitrary x next to that 10 saying we could either decrease the price by 10 like 4 times, or we could increase the price by 10 4 times. We don't really know. The quantity, it originally starts with 90 jackets being sold, and then there is an addition of 5 more jackets, but we just don't know how many additions of 5 there are. So they could sell 4 more times of 5, which is 20 jackets more. They could sell 5 less more in that case. We look at this and we say it is either going to add 5 groups of 5 or subtract groups of 5, depending on what this x value ends up becoming. Now, when we expand this out, 200 times 90, this is going to give us 18,000. We go 200 times 5, this is going to give us plus 1,000. And more importantly, 1,000x. 10 times 90 is negative 900x. And then we have 10 times 5, which is negative 50x squared. All right, collecting the like terms, we're going to write this as negative 50x squared 1,000 minus 900 is equal to positive 100x, and then plus 18,000 for this other piece here. Okay, this is what we call our revenue equation. And not even revenue equation, but revenue function at this point. Because remember, we're defining this purely as there could be any x that goes into this number here. And so we're just going to make sure that we classify this as the general revenue function. For any x value, there might be some output. Now, find the number of jackets sold to give a specific revenue of 17,600. So when we look at this piece here, what we're going to do is take our revenue statement or our revenue function and then plug this into the revenue and solve it as an equation. Now, they actually ask us to do the following. Choose two algebraic methods, either the factoring, completing the square, or quadratic formula, and you can show that through any of these methods, you get the same solution in terms of how many jackets they should sell for that given revenue. All right, what we're going to do is we're going to first of all do the following. I'm just going to set up the equation and we're going to do the factoring method first and foremost. Factoring method. So method number one, we're going to take that equation of 1760, which is the revenue, is equal to negative 50x squared plus 100x plus 18,000. Now, in order to make this an equation, we're going to subtract that 1760 from both sides. So 1760 moves, 1760 from this side moves. Now what we're going to write this as is 0 is equal to negative 50 x squared plus 100x. And then this is going to be plus 400. There we go. Now, what we can do is something interesting. In the functions unit, because one side was equal to 0, let's divide them all by a common term if possible. I'm going to divide these all by negative 50. When I divide these all by negative 50, what's going to happen is that not only are the signs going to flip, but I'm also going to get a situation where it's 0 is equal to, we reduce this, 50 divided by 50 is just x squared, 100 divided by negative 50 is negative 2x, 400 divided by negative 50 is negative 8, and here's our new quadratic. Now, to factor this, we can do it by inspection because the coefficient is 1. We multiply to make negative 8, add to make negative 2. The two numbers that can do this for me are negative 4 and positive 2. So I'm going to rewrite this as 0 is equal to x minus 4 and x plus 2. We can take these from our quadratic equation unit and write them both equal to 0. So x plus 2 is equal to 0, x minus 4 is equal to 0. When we isolate these for those values, so x minus 4 is equal to 0, let's just clean that up a little bit. I'm going to add 4 to both sides, giving me x equals 4. I'm going to subtract 2 from both sides, giving me x equals negative 2. Here's my solutions here. And so from here, if these are my solutions, then the quantities that we're going to get are the following. From the above, quantity is equal to the 90 ski jackets that we sell plus 5 times the x value. Well, for this one, we have two different situations. We have 90 plus 5 times 4, which is going to be equal to 90 plus 20, which is 110 jackets. Or we're going to get quantity is equal to 90 plus 5 times negative 2, or 90 minus 10, gives us 80. So therefore, they should sell 110 or 80 ski jackets to make $17,600. There it is. Perfect. So our solution comes together. So this is one method we could do. We could do the factoring method, which is totally fine. It's an algebraic method, so great. Fantastic. The other method we could do is completing the square. So what we're going to do is we've actually done a lot of the groundwork already. I'm going to go up here and I'm going to take this simplified function of this one here, or simplified equation, I should say, because function implies that there's some sort of output in terms of a general term. We're going to take this simplified equation we've done a lot of the groundwork on and then complete the square on it to figure out that we can do that method as well in terms of an algebraic method. So method number 2, we take the x squared minus 2x minus 8 is equal to 0. We're going to factor, or we're going to do the complete the square method. Completing the square means we must group our first two terms together and leave our constant outside. Once we have a GCF out, which in this case there is not an ability to do, we're going to go b divided by 2 all squared, which is equal to negative 2 divided by 2 squared, which is equal to negative 1 squared, which is equal to 1. Now from here, we're going to write this as x squared minus 2x plus 1 minus 1. Outside the bracket, the negative 8 stays there. Now, to remove this negative 1, we know we have to multiply it by the coefficient here, but there is no coefficient, so I'm going to write this as x squared minus 2x plus 1. Minus 1 just goes outside with the negative 8. Now we're going to write this as x. We know that our b divided by 2 term appears as the factor of the trinomial. If that's negative 1, I'm going to write this trinomial as x minus 1 squared. Negative 1 and negative 8 make negative 9 equals 0. Now I'm going to add 9 to both sides. When I add 9 to both sides, that's going to make this equation x minus 1 all squared, which is equal to 9. We're going to square root both sides, square root and square root. This is going to give me x minus 1 is equal to plus or minus 3, because when we take the square root, it must be the positive and negative case. And then we get the two following solutions. X minus 1 equals 3. X minus 1 is equal to negative 3. We get x is equal to x plus 1 from the other side, because we want to make sure we move it across. So I'll actually annotate that on both sides. If we add 1 to both sides, I get x equals 4. On my other side, I get x equals negative 2. Hey, look at that. We get the same x values that we did in the factoring method. So you see that in part 1, part 2, look at them. They're the same. X equals 4, x equals negative 2, meaning we actually get not only the same amount of ski jackets from part 1, but we also get the same amount of ski jackets from method number 2. Our last and final method is the quadratic formula. We're going to take that same formula that we've put together, or that same equation that we've simplified from part 1, and we're going to take that and then just plug it into our quadratic formula, which is our third and final algebraic method, to show that we should get the exact same numbers. So option number 3, we're going to write this as the x squared minus 2x minus 8 is equal to 0. And then again, realistically, if this was starting from scratch, we'd have to start with that original trinomial and then do all the division, like in terms of that original statement. So what I mean by that is we'd have to take this piece here and then work them to one side, maybe divide by a common factor. But because we already have this and we know that we're going to be trying all different methods, we're just going from this base point here. All right, I go down here. This is x squared minus 2x minus 8. I want to establish an a, b, and c. A is equal to 1 because our coefficient on the x squared is 1 here. We're going to write our b is negative 2 because we pulled the term with it. C value, the constant, is negative 8. Now when we go to our quadratic formula, it's x is equal to negative the b value plus or minus the square root of negative 2 squared, which is b, minus 4 times 1, which is a, negative 8, which is c, all divided by 2 times the a value, which is 1. Now, let's see what type of room I have to deal with. Yeah, I'm going to bring it up here. So if I go somewhere about here, I'm going to continue this as x is equal to positive 2 plus or minus the square root of. This, in the internal side of the bracket, is going to give me 4 plus 32, which is actually the square root of 36, all divided by 2 times 1, which is just 2 from the denominator. This gives me x is equal to 2 plus or minus the square root of 36, which is 6, divided by 2, and therefore my two solutions, we need to do one of them. X is equal to 2 plus 6 over 2, which is equal to 8 divided by 2, which is equal to 4. My other solution is x is equal to 2 minus 6 over 2, which is equal to negative 4 over 2, which is equal to negative 2. Hey, look at that. We get the x equals 4, the x equals negative 2 that we saw in all the other parts. Look at that. We'll zoom out on these in the grand scheme of things. So no matter which direction we go algebraically, you're going to find that you can solve it. Now, there's going to be some that are better methods than other in certain situations, but for this situation, it really didn't matter what we picked. We could have done them all. And what I'm going to do to wrap this up is just arrow up from that last part here and just say that this is also an alternative solution that would give us to the same amount of ski jackets that should be sold. Okay, now here's where you want to move on to your assignment. Your assignment is listed in the bottom here. Textbook questions, try them out. Do as many as you can. This is actually the last lesson for quadratic equations. You now have to look forward to your unit tests. So I'll be giving out lots of review material to help you out, but the textbook's also there to support you. All right, good luck with your practice.